Hi guys, tonight we're diving into one of the most mind-bending scenarios yet. What would happen if we could somehow drain all the water from Earth's oceans? I'm talking about exposing the hidden landscape of the ocean floor and watching as our entire planet transforms into something completely alien. If you're enjoying these deep dive sleep stories that explore wild scientific what-ifs, hit that like button and subscribe so you never miss an episode, and drop a comment below letting me know what time it is, where you are, and where you're listening from. I love seeing all you fellow night owls from around the world. Alright, let's begin. You stand at the edge of the Pacific Ocean and watch waves roll toward shore, each one carrying energy that originated perhaps thousands of kilometers away. The water stretches to the horizon, blue meeting sky in a line so distant you can see the curve of the Earth. Below that surface lies an average depth of 4,000 meters, and volume of water so vast it contains roughly 1.335 billion cubic kilometers. That's 1,335 million liters, a number so large it becomes meaningless until you try to imagine removing it. What if you could open some cosmic drain and let all that water flow away, exposing the true shape of the ocean floor that has remained hidden beneath kilometers of water for hundreds of millions of years? The transformation would reveal a landscape stranger and more dramatic than any mountain range on dry land, but the consequences would extend far beyond geography. Draining the oceans would dismantle the machinery that makes Earth habitable, setting in motion a cascade of changes that would transform our planet into something alien and hostile within weeks. The first challenge is purely mechanical. Where does the water go? We need to move 1.335 billion cubic kilometers somewhere. If we're thinking about draining it into space, launching it beyond Earth's gravitational pull, the energy requirements become astronomical. Water has a mass of 1,000 kilograms per cubic meter, meaning the oceans weigh approximately 1.386 times 10 to the power of 21 kilograms. That's 1 billion trillion metric tons. To escape Earth's gravity, each kilogram needs to reach escape velocity of 11.2 kilometers per second, requiring roughly 62.6 megajoules of energy per kilogram. Multiply that by the ocean's total mass, and you need roughly 8.68 times 10 to the power of 28 joules of energy. For context, total human energy consumption in 2020 was approximately 580 exajoules. That's 5.8 times 10 to the power of 20 joules. To drain the oceans into space would require roughly 150 million years of current total human energy output, assuming perfect efficiency with no energy losses, which is physically impossible. Even if we covered every square centimeter of Earth's surface with perfectly efficient solar panels, capturing all incoming solar energy, approximately 173,000 terawatts, it would take roughly 15,000 years to accumulate enough energy. This is clearly beyond any conceivable technology, so let's instead imagine that the water simply vanishes, removed by some mechanism that requires no energy input. Now we can focus on what happens to Earth itself. The transformation begins the moment water levels start dropping. Coastal areas emerge first, revealing continental shelves that have been submerged for millions of years. The continental shelf extends from the shoreline to depths, averaging about 130 meters, though it varies regionally. Off the coast of Siberia, the shelf extends up to 1,500 kilometers from shore before dropping off into deeper water. As water levels drop those first 130 meters, roughly 28 million square kilometers of new land appears, an area roughly equivalent to the continent of Africa. This exposed shelf would be muddy, littered with shipwrecks from thousands of years of maritime history, and initially covered with the dying remains of shallow water marine ecosystems. At minus 130 metres, the English Channel becomes dry land. Britain reconnects to continental Europe, as it was during the last ice age, when sea levels were 125 metres lower than today, creating the land bridge called Doggerland. The North Sea shrinks dramatically. The Persian Gulf vanishes entirely, exposing the river valleys of the Tigris and Euphrates, extending far beyond their current mouths. The Mediterranean Sea begins to separate into smaller basins as shallow sills emerge between deeper areas. The Strait of Gibraltar, roughly 300 metres deep at its sill, still allows water to flow between the Atlantic and Mediterranean, but connections between eastern and western Mediterranean basins become restricted as shallower passages emerge. Continue draining. At minus 500 metres, the Indonesian archipelago connects into massive land bridges. The shallow Java Sea, Arafura Sea, and much of the area between Southeast Asian islands emerges, creating continuous land from mainland Asia to New Guinea and nearly to Australia. This recreates the prehistoric landmass of Sunderland that existed during Ice Age low sea levels. The Caribbean Sea shrinks dramatically as shallow banks between islands emerge. The Bahamas platform, currently submerged beneath only a few meters of water over vast areas, becomes a massive limestone plain. The climate impacts begin immediately. The oceans contain 97% of Earth's water and cover 71% of the surface. They act as the planet's primary thermal regulator, absorbing heat during the day and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. Absorbing heat in summer and releasing it at night. absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and releasing it at night, absorbing heat in summer and it in winter, absorbing heat at the equator and transporting it toward the poles through currents. Ocean water has a specific heat capacity of approximately 4,182 joules per kilogram per degree Celsius, roughly 4 times higher than rock or soil. This means oceans can absorb or release vast amounts of heat with relatively small temperature changes, buffering atmospheric temperature swings. When you remove this thermal mass, daily and seasonal temperature fluctuations become extreme. Coastal areas that currently experience moderate climates due to ocean proximity, where temperature ranges might be 10 to 15 degrees Celsius between summer and winter, would suddenly experience continental climate patterns with temperature ranges of 30 to 50 degrees Celsius or more. San Francisco, which currently ranges from average lows of 8 degrees Celsius in winter to highs of 21 degrees Celsius in summer due to Pacific Ocean moderation, would experience temperatures more like interior California, desert locations with winter freezes and summer heat exceeding 45 degrees Celsius. The global climate system depends critically on ocean heat transport. The Gulf Stream carries approximately 1.4 petawatts of thermal energy northward, warming Western Europe by an estimated 5 to 10 degrees Celsius above what its latitude would suggest. When the oceans drain, this heat transport vanishes. Within weeks, as autumn transitions to winter in the Northern Hemisphere, Western Europe experiences temperatures plummeting far below normal. London, Paris, Berlin, cities at latitudes equivalent to southern Canada, face winters without ocean moderation. Average January temperatures that currently hover around freezing could drop to -20 or -30 degrees Celsius, similar to Siberian conditions. At -1,000 meters of ocean level, the drainage has removed roughly 15% of ocean volume. The continental shelves are completely exposed. The major ocean basins remain full, but isolated basins are beginning to emerge. The Red Sea, with a maximum depth of around 3,000 meters, but a shallow sill of only 137 meters, connecting it to the Indian Ocean, has become landlocked and is rapidly evaporating. The Mediterranean Sea has separated from the Atlantic as the Strait of Gibraltar's deepest point, approximately 900 meters, is now exposed. The Mediterranean becomes a closed basin, and here we witness something that actually happened in Earth's history. Between 5.96 and 5.33 million years ago, during the Messinian salinity crisis, the Strait of Gibraltar closed due to tectonic uplift. The Mediterranean, receiving less water from rivers than it lost to evaporation, dried up almost completely in perhaps as little as 1,000 years. The basin's floor, lying up to 5,000 meters below sea level in places, became a massive salt desert as salt precipitated from the evaporating water. Rivers including the Nile, Rhone, and others carved deep canyons into the exposed basin, with the Nile cutting a canyon extending more than 1,400 meters below its current delta. When the strait reopened, the Mediterranean refilled catastrophically with water pouring in at rates that may have exceeded 100 million cubic meters per second, filling the entire basin in as little as 2 years. In our drained ocean scenario, this happens to multiple basins simultaneously. The Mediterranean, Black Sea, Red Sea, Persian Gulf all become isolated evaporating basins. The salt dissolved in seawater, approximately 35 grams per litre, begins precipitating out. Each cubic kilometre of seawater contains roughly 35 million tons of salt. As these enclosed basins evaporate, they leave behind massive salt deposits. The Mediterranean alone, with a volume of roughly 3.75 million cubic kilometres, would deposit approximately 130 billion tons of salt across its floor, creating deposits hundreds of meters thick in the deepest areas. At -2,000 meters, roughly 40% of ocean volume has been removed. Now the landscape revealed becomes truly alien. The mid-ocean ridges, volcanic mountain ranges that wind through all the world's oceans for a combined length of approximately 65,000 kilometers, emerge from the water. These ridges, where tectonic plates diverge and new oceanic crust forms through volcanic activity, rise 2 to 3 kilometers above the surrounding abyssal plains. The mid-Atlantic ridge running down the center of the Atlantic Ocean from Iceland to Antarctica becomes a massive mountain range bisecting what remains of the Atlantic. Iceland, which sits atop this ridge, now rises as a high peak in a continuous mountain chain. The exposed ridge systems would be geologically active, studded with volcanic vents, hydrothermal vents called black smokers, where superheated water at temperatures exceeding 400 degrees Celsius erupts from the seafloor. These vents, previously underwater, now spew their mineral-rich fluids into the air, creating bizarre formations of metal sulfide deposits, creating toxic chemical clouds that drift across the exposed ocean floor. The ecosystem of tube worms, giant clams, and specialized bacteria that inhabited these vents, surviving on chemosynthesis rather than photosynthesis, dies within hours of exposure. These creatures, some of which have been isolated at deep-sea vents for millions of years, evolving into unique species found nowhere else, go extinct before a scientist can study them. The abyssal plains, flat expanses of the deep ocean floor between 4,000 and 6,000 meters depth, emerge as vast muddy deserts. These plains cover roughly 40% of Earth's total surface, larger than all the continents combined. They're covered in sediment accumulated over millions of years, oozes made of the microscopic shells of dead plankton, clay particles, and cosmic dust that constantly rains down from space. This sediment can be several kilometers thick in places. When exposed to air, the surface layer dries and begins to blow away as dust. The finest particles, smaller than 10 micrometers, become airborne, creating massive dust storms that spread across the planet. The atmospheric consequences escalate rapidly. The oceans currently produce approximately 50 to 80% of Earth's oxygen through phytoplankton photosynthesis. When the oceans drain, all marine phytoplankton die within hours. These microscopic organisms, including cyanobacteria like Prochlorococcus and diatoms, produce between 100 and 150 billion tons of oxygen annually. Their sudden death removes half or more of Earth's oxygen production. The remaining oxygen production from terrestrial plants, roughly 50 billion tons annually from rainforests, grasslands, and other vegetation, cannot compensate for this loss. Atmospheric oxygen content currently stands at approximately 21%, or about 1 quintillion tons of oxygen in the atmosphere. Losing half the annual production doesn't immediately deplete oxygen levels, but over time the impact compounds. Without ocean oxygen production, and with continued consumption by animal respiration, decomposition, and combustion, atmospheric oxygen would gradually decline. Over decades to centuries, oxygen levels could drop to 18 or 17%, still breathable for humans but noticeably different, similar to being at moderate altitude. Strenuous activity becomes more difficult. People with respiratory conditions suffer more severe symptoms. The carbon dioxide problem is more immediate. The oceans currently absorb approximately 25 to 30% of the carbon dioxide that humans emit, roughly 10 billion tons of carbon dioxide annually. This dissolved carbon dioxide exists in chemical equilibrium with atmospheric carbon dioxide. When the oceans drain, this equilibrium breaks catastrophically. The carbon dioxide dissolved in ocean water, approximately 38,000 gigatons of carbon compared to 850 gigatons in the atmosphere, suddenly has nowhere to go. Some would be released as gas during the draining process, especially from warming surface waters. but much of it is chemically bound as carbonate and bicarbonate ions that precipitate out as the water evaporates. However, the loss of ocean carbon absorption capacity means that atmospheric carbon dioxide begins accumulating faster. Current atmospheric carbon dioxide concentrations around 420 parts per million would begin rising at accelerated rates, perhaps reaching 500 or 600 parts per million within decades. This enhances the greenhouse effect, warming the planet even as the loss of ocean thermal moderation creates extreme temperature swings. The combination creates a climate unlike anything in recent Earth history, combining extreme temperature variability with overall warming. At minus 4,000 meters, we've removed roughly 75% of ocean volume. The major ocean basins are now shallow lakes in the deepest trenches. The Pacific Ocean, once covering 165 million square kilometers, has become a series of isolated bodies of water sitting in the deepest parts of the basin. The deepest of these is the Mariana Trench, extending to 10,984 meters below original sea level. The Challenger Deep, the deepest known point, now sits at the bottom of a narrow chasm nearly 11 kilometers below the former sea surface. The trenches form along subduction zones where oceanic plates dive beneath continental or other oceanic plates. Their dynamic geological features actively being compressed and deformed by tectonic forces. The Mariana Trench is currently being compressed at a rate of about 5 to 7 centimeters per year as the Pacific Plate subducts beneath the Philippine Sea Plate. With a weight of 4,000 meters of water removed from the surface, the pressure on the seafloor drops by approximately 40 megapascals, roughly 400 times atmospheric pressure. This pressure relief would trigger adjustments in the crust. The Earth's crust is in isostatic equilibrium, floating on the denser mantle beneath. Ocean basins are compressed downward by the weight of water above them, similar to how a person standing in a boat makes it sit lower in the water. Remove that weight and the crust begins rebounding upward. This isostatic rebound occurs over thousands of years, but the initial adjustments could trigger massive earthquakes as the crust fractures and shifts. Every subduction zone, every mid-ocean ridge, every fault line beneath what is the ocean floor would experience increased seismic activity. The exposed ocean floor contains features that boggle the mind when you can see them in full. Underwater mountains called seamounts, most of them extinct volcanoes, rise from the abyssal plains. They are estimated to be more than 100,000 seamounts taller than 1,000 meters, with many exceeding 4,000 meters in height. These rival or exceed the tallest mountains on land. Hawaii's Mauna Kea, measured from its base on the ocean floor to its summit, stands approximately 10,200 meters tall, taller than Mount Everest's 8,849 meters above sea level. When the oceans drain, Mauna Kea becomes Earth's tallest mountain by a substantial margin, rising nearly 11 kilometers from the surrounding plain. The Hawaiian Islands are just the visible peaks of a massive volcanic chain, the Hawaiian Emperor Seamount Chain, extending over 6,000 kilometers across the Pacific floor. This chain formed as the Pacific Plate moved over a volcanic hotspot, creating a new volcano every few 100,000 years, each building from the seafloor until some broke the surface as islands, while others remain as seamounts. Exposed, this chain becomes one of Earth's most spectacular mountain ranges, thousands of peaks stretching in a line across the basin. The biological consequences are absolute. Every marine species that hasn't already died from desiccation or oxygen deprivation now faces extinction. Approximately 240,000 known marine species exist, but estimates suggest the true number might exceed 2 million species when you include all the undiscovered species in deep ocean environments. All of them die. Every whale, dolphin, seal, and sea otter. Every species of fish, from tiny gobies to massive ocean sunfish. Every invertebrate, from microscopic zooplankton to giant squid that might reach lengths of 13 meters. Every coral, sea anemone, jellyfish, sea star, sea urchin, mollusk, crustacean, and marine worm. The oceans have hosted complex life for over 500 million years, surviving multiple mass extinctions, but they cannot survive this. On land, the ecosystem collapse spreads from the coasts inward. Seabirds that depend on ocean fish for food starve within days. Albatrosses, which can fly for thousands of kilometers across the open ocean hunting for squid and fish, die as their food sources vanish. There are 22 species of albatross, most of them already threatened by fishing bycatch and plastic pollution. All go extinct. Penguins, which exist in 17 species ranging from Antarctic penguins that never encounter humans to endangered species like the Galapagos penguin, die within weeks. Emperor penguins, which can dive to depths of 560 meters and hold their breath for over 20 minutes while hunting fish and squid, have nothing to hunt. The entire population of roughly 600,000 individuals starves. Coastal ecosystems that depend on marine nutrients collapse. Seabird colonies that deposit nitrogen and phosphorus-rich guano on coastal rocks have supported vegetation and terrestrial food webs for thousands of years. These nutrient inputs vanish. Salmon and other anadromous fish that migrate from ocean to rivers can no longer complete their life cycles. Pacific salmon species that bring marine nutrients far inland when they return to spawn, supporting grizzly bears, eagles, and forest ecosystems through their nutrient-rich carcasses, disappear. Grizzly populations in Alaska and British Columbia that depend on salmon for up to 90% of their nutritional intake during spawning season face starvation. The human consequences are catastrophic beyond the earlier scenarios we explored with dying fish populations, because now we lose not just the marine life, but all the other ecosystem services the oceans provide. 360 million jobs are directly or indirectly linked to ocean resources, not just fishing, but tourism, shipping, offshore energy, and more. Global shipping, which carries 90% of world trade by volume, approximately 11 billion tons of goods annually, becomes impossible. Ships cannot sail across exposed ocean basins. Trade routes that connected continents for thousands of years vanish overnight. The economic impact exceeds any disaster in human history. Global GDP, approximately $94 trillion in 2021, would collapse by perhaps 50% or more within months as supply chains disintegrate. Modern economies depend on just-in-time delivery of goods and components from around the world. Without shipping, factories shut down for lack of parts. Store shelves empty. Medicines, electronics, food, everything that moves by sea cargo becomes unavailable outside its region of production. Countries that import most of their food face immediate famine. Japan imports roughly 60% of its food by caloric intake. Without shipping and without seafood, Japan faces starvation of tens of millions, unless emergency measures establish new supply routes. Air freight and overland transport cannot compensate for the loss of shipping. Container ships carry thousands of 20-foot equivalent units at costs of roughly $50 to $100 per ton for intercontinental routes. Air freight costs approximately $4 to $8 per kilogram, roughly 80 times more expensive. You cannot economically fly the billions of tons of cargo that ships move annually. Most products that currently trade internationally would become economically impossible to transport. Only high-value, low-weight goods like electronics and pharmaceuticals could justify air freight costs. The climate continues deteriorating. Without ocean evaporation, the water cycle changes fundamentally. The oceans currently contribute approximately 85% of atmospheric water vapor through evaporation, roughly 535,000 cubic kilometers of water annually. This water vapor falls as precipitation over land and ocean, with approximately 115,000 cubic kilometers falling on land. Rivers return roughly 45,000 cubic kilometers to the ocean annually, while the rest falls back on the ocean or is stored in groundwater and ice. When ocean evaporation stops, the source of most atmospheric moisture vanishes. Rainfall over land drops dramatically. Only water that evaporates from lakes, rivers, soil, and vegetation remains in the cycle, perhaps 15 to 20% of current atmospheric moisture. Precipitation declines proportionally. Areas that currently receive 1,000 millimeters of rain annually might receive just 150 to 200 millimeters, transforming them into deserts. The Amazon rainforest, which recycles much of its own moisture through evapotranspiration, but depends on atmospheric rivers carrying moisture from the Atlantic, receives less moisture input. The forest begins dying from the outside in, transitioning to savanna and then desert. Global temperatures swing wildly on daily and seasonal cycles without ocean thermal buffering. But the overall trend is toward extreme heat. The exposed ocean basin floors, covering 71% of Earth's surface, heat up rapidly under direct sunlight. Dark volcanic rock and sediment absorb solar radiation efficiently. Surface temperatures in exposed tropical ocean basins could reach 60 to 70 degrees Celsius during peak afternoon sun, similar to desert surfaces in places like Death Valley. At night, without moisture or thermal mass to retain heat, temperatures plummet to near freezing or below. These extreme temperatures create violent weather patterns. The temperature differentials between day and night, between exposed basin floors and remaining land surfaces, drive powerful winds. Dust storms lift fine sediment from exposed ocean floors, creating dust clouds that can travel thousands of kilometers. These dust storms, far larger than anything currently experienced even in the Sahara, reduce visibility to near zero and deposit thick layers of marine sediment across continents. The dust contains salt, toxic heavy metals, and other compounds that poison soils and water supplies where it settles. At minus 6,000 meters, approximately 90% of ocean water has been removed. Only the deepest trenches still contain water, isolated lakes in the bottom of chasms. The Mariana Trench holds water perhaps 4 to 5 kilometers deep in its deepest sections. This water, now exposed to the atmosphere but sitting so far below the surrounding landscape that sunlight barely penetrates the trench, begins evaporating slowly. It's also become a chemical soup. All the salt that was dissolved throughout the ocean has concentrated into these final pools. The salinity might be 10 or 20 times normal seawater, approaching saturation where salt crystals begin precipitating out. Any life that somehow survived in these remnant pools cannot persist. The salinity is far beyond tolerance ranges even for hypersaline-adapted organisms. The temperature fluctuations are extreme. The chemical composition is toxic. The last marine organisms on Earth die in these shrinking pools at the bottom of the world's deepest trenches, surrounded by walls of rock rising 11 kilometers on either side. never seeing the sky that their ancestors swam beneath for hundreds of millions of years. The final drainage takes months or years as evaporation slowly removes the last water from the trenches. The process leaves behind salt deposits kilometers thick in some locations. These deposits, containing all the minerals and elements that were dissolved in seawater, represent a geological resource of staggering scale. There's enough sodium chloride to create a salt layer roughly 60 meters thick if spread across the entire ocean floor. But there's also massive deposits of magnesium, calcium, potassium, and trace amounts of gold, silver, uranium, and virtually every other element on the periodic table. The ocean floor becomes a mine of nearly unlimited mineral resources, though in a world where global trade has collapsed and human civilization is fighting for survival, few resources exist to exploit it. Earth's rotation is affected subtly. The oceans, through tidal friction with the moon, gradually slow Earth's rotation by approximately 1.5 to 2 milliseconds per century. This has been happening since the moon formed roughly 4.5 billion years ago. Early Earth, before the moon formed, likely rotated much faster, with days perhaps 5 to 6 hours long. The moon's gravitational pull creates tidal bulges in both the oceans and the solid Earth, but ocean tides are much larger and dissipate more energy. Without oceans, tidal energy dissipation drops dramatically. Earth's rotation still slows due to solid Earth tides, but at perhaps 10% the current rate. Over millions of years, this would mean Earth retains faster rotation than it otherwise would, but the immediate impact is negligible. The moon itself experiences changes. The moon is gradually receding from Earth at approximately 3.8 centimeters per year, driven by tidal interactions that transfer angular momentum from Earth's rotation to the moon's orbit. Reduced tidal friction means this recession slows. Again, the short-term impact is tiny, but over millions of years the moon's orbit would be noticeably closer to Earth than it would have been with oceans present. Tides themselves, the twice-daily rise and fall of sea level, obviously vanish with the oceans, but solid Earth tides continue, raising and lowering the ground by up to 55 centimeters, though we cannot perceive it without instruments. The exposed ocean basins begin filling with sediment from erosion of surrounding land masses. Rivers that once emptied into the ocean now flow down steep escarpments onto the former seafloor, dropping thousands of meters in spectacular waterfalls before spreading across the basins. The Nile, Amazon, Yangtze, Mississippi, all the world's major rivers, cut deep gorges into the continental margins and deposit their sediment far out on the exposed abyssal plains. The sediment deposition rates would be extraordinary. Major rivers carry billions of tons of sediment annually. The Amazon alone carries approximately 1.3 billion tons of sediment per year. Without oceans to disperse this sediment across vast areas, it piles up in localized deposits near river mouths, building massive alluvial fans and deltas. The Earth's albedo, its reflectivity, changes substantially. The oceans currently reflect only about 6% of incoming solar radiation, absorbing the rest. The exposed ocean floor, covered in dark volcanic rock and sediment, would have higher albedo, perhaps 15 to 20%. This means more solar radiation reflects back to space, providing slight cooling feedback against the greenhouse warming from increased carbon dioxide. However, this is insufficient to counteract the overall warming trend. Global average temperatures, currently around 15 degrees Celsius, would likely rise by 10 to 15 degrees Celsius over decades to centuries, even while daily and seasonal temperature swings become far more extreme. Life on land struggles to adapt to the transformed world. Plant communities shift dramatically as rainfall patterns change and temperature extremes increase. Forests die in many regions, unable to tolerate the new conditions. Grasslands and deserts expand. The species extinction rate, already elevated by human activities, accelerates catastrophically. Large mammals with high food requirements and slow reproduction rates decline rapidly. Elephants, rhinoceroses, big cats, bears, most large herbivores and carnivores face extinction within decades as habitats fragment and food sources decline. Smaller, more adaptable species like rodents, insects, and some birds might persist, but biodiversity crashes globally. Human populations decline precipitously. Without seafood, without reliable rainfall for agriculture, without trade networks to distribute food, carrying capacity drops dramatically. Current global population, around 8 billion people, depends critically on modern agriculture, which feeds approximately 7.6 billion people beyond what hunter-gatherer subsistence could support. Remove ocean fish, reduce rainfall by 80%, eliminate international food trade, and carrying capacity might drop to 1 or 2 billion people, or fewer. The death toll from famine would be measured in billions. Societies would collapse into regional fragments struggling for survival. Technology would regress as supply chains break and specialized manufacturing becomes impossible. Some regions would fare better than others. Areas with reliable river water, enough remaining rainfall for agriculture, and geographic isolation from competition might sustain viable populations. The Great Lakes region, the Mississippi watershed, the Yangtze Basin, areas around large freshwater lakes in East Africa. These might support human populations if they can defend their resources and develop self-sufficient food production. But most of humanity's current population centers, particularly coastal cities that have depended on ocean proximity for trade and climate moderation, would become uninhabitable. In the very long term, over millions of years, the planet might eventually develop new equilibria. Volcanic activity would continue releasing water vapor and carbon dioxide from Earth's interior. This water vapor would condense as rain and eventually begin filling the ocean basins again, though the process would take millions of years to accumulate enough water to create anything resembling oceans. By that time, any surviving life would have evolved to adapt to the hostile conditions, perhaps developing new ecosystems fundamentally different from anything that existed before. Evolutionary processes would continue, and given enough time, life might even return to the refilling oceans, beginning the long process of diversifying into marine ecosystems once again. But this is cold comfort on human timescales. For any generation alive when the ocean's drained, for their children and their children's children for dozens of generations, Earth would be a dying world, hostile and impoverished compared to the lush blue planet that existed before. The oceans are not just features of Earth's surface, they're integral to planetary functioning. They regulate climate, produce oxygen, support biodiversity, enable trade, provide food, and maintain chemical cycles that keep the atmosphere and land habitable. Remove them, and you remove the foundation of everything that makes Earth the unique, life-rich world it is. The thought experiment reveals our profound dependence on systems we rarely think about. The oceans seem permanent, unchanging except for tides and waves, but they are dynamic systems constantly in motion, constantly interacting with atmosphere and land, constantly supporting the web of life that extends from their depths to the tops of mountains. We are creatures of the oceans even when we live far inland, breathing oxygen they produce. Eating food grown with water, they evaporate. Living under climate patterns, they stabilize. To drain them would be to drain the life from Earth itself, leaving behind a husk of a planet where survival becomes a daily struggle, and the memory of blue water stretching to the horizon becomes a myth from a better age that can never return.